I tried to with my final model and using the turn it into something new.
Yeah, we'll probably, it'll be marked pretty easily, I think. As long as you sort of indicate to us that that you roughly got it, that you know what you're doing. Yeah. All right. All right. So I'm going to get started here. It's September 25th. So yeah, you guys should have handed in your assignment ones. Who found assignment one difficult? A lot of people. Yeah. Okay. I guess, well, once we get the marks back, we can start to identify maybe what, what parts you found difficult. Is there any particular question that was, or questions that were easy and questions that were hard? I mean, I have my own opinion, but. Was it the dogs in the cages? Was that the hardest one? Yeah, that was a tricky one. But you could brute force that, right? That's, yeah. Anyway, we could, maybe after pigeonhole, I think is a little short. So after, if anybody wants to take up some of the assignment questions, we can do that. I'm going to, I just sent Pat an email this morning, and once he gets back to me, then we'll do things like release the solutions and actually, I guess I could release the solutions, but then, and release assignment two. Assignment two is ready, except Pat's proofreading it for me. It's not due for, I guess, what, 3 weeks or something, but yeah, it should be released sometime today, maybe tomorrow at the latest. But yeah, all right. Any questions? Sorry?
I'm going to start first.
Yeah. I mean, assignment two might be harder than assignment one. Just throwing that out there. But I mean, the purpose of the assignments is to learn the material, right? Most of the marks are on the midterm and the final. So I wouldn't get too hung up on if you missed a couple marks here or there. You're going to be fine.
Just test my knowledge on the concept.
Well, yeah, you have to do some exercises before you can, you got to train that part of your brain basically. And then anyway, so yeah, today we are going to talk about the pigeonhole principle, which is sort of a really simple concept, but it has some interesting applications where it's sort of more useful than you would think in a lot of cases. So yeah, let's talk about that. Okay, so let's start with an example. If we have 365 people, can we say for certain whether or not anybody shares a birthday? Right, forgetting leap years at this point. But in general, we'll get to the birthday paradox later, which is, which shows when you have about 23 people, you got about a 50-50 shot that two people share a birthday. But just because it's probable doesn't mean it's always the case, right? So if I have 365 people, and let's say I have my calendar, and each day on my calendar, I write down whose ever birthday it is possible that I fill in this entire calendar and nobody shares a birthday, right? I can have exactly one person having a birthday on any given day. So, me, well, no, I'm not January 1st, but I'm in January. I don't know, Bob, Alice. And then I fill it all in, and at the end, I only have at most one person per day. But then what happens if I do the same thing and it's not a leap year, or no, let's say none of these people are born on February 29th. So I have 366 people and 365 days. So now, yeah, it's guaranteed that at least two people will share a birthday, right? So it's probable that we will have a lot more people sharing a birthday, but I can say with a certainty that at least two of these 366 people will share a birthday. And why is it? Well, I mean, you can just sort of you know, you start writing people's birthdays down and then assume that no two people are on the same day, then after I get through 365 people, I still have one person left that I have to place. So yeah, that's in the simplest form, that's the pigeonhole principle, and it's, you know, it seems almost trivial, but it does have some really weirdly interesting applications. Okay, so let's do another example. So let's say we're in a country where everyone's last name is composed of one uppercase letter and one lowercase letter. Right, so here are some examples. This is similar to like creating passwords or any sort of string. And we've counted things like this before. So the claim is that in a country with at least 677 people, at least 2 people must have the same last name. Okay, so why is that? Well, let's start by counting the number of people, or sorry, the number of unique last names. So how many unique last names do we have here? Yeah. Yeah, so I have 26 choices for the first letter and 26 choices for the second letter. So I have 26 times 26, which is 676. But yeah. And then I have 677 people. So if again, I'm going to make instead of a calendar now, I'm just going to have a list of all of the possible last names. And then I will, every time I find somebody that has one of them, I'll just tick that off. And then it's guaranteed that at least one of these locations will have 2 tick marks in it. You know, Mr. AB and Mrs. AB both go in this slot. Okay, so that, again, this is this concept of we have these like slots or boxes or places that we can put things, and then we have a bunch of things to be placed, right? So when we talk about the pigeonhole principle, these holes or bins or what have you are known as the boxes, and the pigeons are known as the pigeons, right? So we have K plus 1 pigeons and K holes. And then, so for any sort of general example of this, if I have, or if I can sort of define a bunch of boxes and a bunch of things to go in them, and I have at least one more thing that goes in the holes, then I have objects, then there's going to be one box or one hole with 2 pigeons. Okay, so we can prove it by contradiction, right? So our claim is that there exists a hole with at least 2 pigeons. If we want to prove it by contradiction, we're going to take the negation of that statement. So we're going to say there does not exist a hole with at least 2 pigeons. And then we will, you know, similar to what we used to do in 1805, we're going to negate this quantifier, which will flip it into for all holes. And then there does not exist at least 2 pigeons, which if I translate that into English, it means every hole has at most 1 pigeon. And if every hole has at most 1 pigeon, then there can be at most K pigeons, right? Since there are at most K holes, I have at most K pigeons, but this directly contradicts the thing that I know to be true, which is I have K plus 1 pigeons. So that's proof by contradiction. So that means my original statement that I negated here was true, right? So I negated it, and I proved that the negation was false, so that that means the original statement was true. So there exists a hole with at least 2 pigeons. Yeah. Intuitively, you can just sort of try to construct a counterexample, right? You just start putting things into boxes until all of your boxes are full, and then you'll see that you have one more pigeon left, and so that pigeon has to go into a box that already contains another pigeon. Okay, so that's the pigeonhole principle. Sort of simple, but any questions? Okay. let's try, so those are some sort of trivial examples. Let's try something slightly more complex. Incidentally, you did kind of use the pigeonhole principle on your first assignment, right? Well, I'll show you at the end. We'll take up at least question 1, right? So I don't know. Arguably, maybe not fair to throw the pigeonhole principle at you before we took it, but again, we're going to mark it kind of easy, so don't fret. Let's say I take all of the numbers 1 through 2 times n, right? So n is some integer, and I'm going to take a subset of those numbers. And this subset, which I call S, has size n plus 1. Okay, and we'll look at an example of this to see exactly what I mean by this. But then my claim is that among all of these numbers, there exists 2 numbers, a and b, such that a minus b is equal to 1. Right? Another way to say that is, of course, a and b are consecutive. Right? So maybe a is equal to 3 and b is equal to 4. I mean, this is, I guess I should label them the other way. Right, so yeah, they're consecutive numbers. So if I subtract one from the other, I get 1. But yeah, so we want to solve this using the pigeonhole principle, or prove this claim using the pigeonhole principle. Right, so this is what we want to prove. And these are the facts that we have in order to prove it. And we want to use the pigeonhole principle, which means we want to sort of make a bunch of boxes and then have things that go in those boxes and show that there's too many things for all the boxes, basically. But yeah, let's try and construct a counterexample here to gain some insight, or construct some examples. So I'm going to find a subset S. I'm going to take n equal to 4, right? So then I'm taking the numbers 1 through 2n. So I have the numbers 1 through 8. And I'm going to take a subset of it of size n plus 1. So my subset here is going to be, did I write it? 5, yeah. So I'm going to take 5 elements, and I'm going to try to do it in a way such that this isn't true. And I'm going to see what happens, right? So trying to construct a counterexample is often a useful exercise, because it reveals a lot of properties about this thing. So I want to choose 5 of these numbers for my subset, and I don't want to choose 2 consecutive numbers, right? If I choose 2 consecutive numbers, then this is true, and I'm trying to construct a counterexample. All right, so yeah, well, if I choose 1, of course, I can't choose 2, so then I can choose 3, but then I can't choose 4, and then I can choose 5, but then I can't choose 6, and then I can choose 7, but then I can't choose 8. And I want to choose 5 total, and I've gotten to 4, and now I've, in some sense, run out of numbers. Any other number that I choose will make this claim true. And I'm trying to construct a counterexample. Okay. Question so far? Yeah. Right. Yeah. Yeah. I mean, yes, so yeah. So you're trying to prove it outside of this, yeah, that this is going to happen. And we're going to try and prove the same thing using the pigeonhole principle. But yeah, you got the right idea. So yeah, let's try that again. Basically, I can choose, right? These are in consecutive order, so I can either choose, every even number or every odd number, essentially. If I have an odd and If I choose all the even numbers, then any one of these odd numbers makes this claim true. And if I choose all of the odd numbers, then any one of these even numbers makes this claim true because they're beside each other basically in this list. So that that exercise of trying to create a counterexample gave us some insight into how we should form our boxes, right? And basically we want to form our boxes such that if I have two elements in the box, then my claim is true for those two elements. Okay, so let's see here. I'm going to make 4 boxes, and in each of my boxes, I'm going to put 2 consecutive elements such that if I end up with a box that has 2 elements, then this must be true. Right, so 1, 2, 3, 4, 5, 6, 7, 8 will come later. It's just the transitions are out of order, or the animations. So I have 4 boxes. Let's write that down until it comes up. And I have my set of 5 elements. In this example, I have a specific example, or I have a specific set of 5 elements, but if I didn't even know what these 5 elements were, I could still tell you for certain that one of these boxes will have 2 of those elements in it by the pigeonhole principle. Right, so I go through, I say 1, well, that goes in here. 3, that goes in here. 5, that goes in here. 7, that goes in here. And then the last one, of course, I've already filled all the boxes, so it has to go in a box that already has a pigeon. So that means my 7 and 8, well, I have 2 numbers that the difference is equal to 1. So my claim is true in this case. And here is sort of proof by example, but even if I didn't know what these numbers were, and I had these 4 boxes, I would still know that any 5 numbers, I must have at least 2 numbers in one of these boxes. Questions? Okay. Yeah. For some reason that got moved to the end of the animations. I'm not sure why. Okay, so now in the general case I have 2 times n elements, and I'm going to choose a subset of size n plus 1. Before n was equal to 4. So I had 8 elements. I chose a subset of size 5, but I can do it in general. I make all of my boxes 2 consecutive elements. So 1 and 2, 3 and 4, 5 and 6, all the way down to, well, I'm going up to 2n. So 2n minus 1 and 2n. So now I have n boxes total, and my subset contains n plus 1 elements. So that means at least one of these boxes must have 2 elements. Those 2 elements have a difference of 1. So that means my claim must always be true. So that's sort of how proof by pigeonhole principle. All right, questions? We'll do a few more examples. So again, we're going to do something very similar. I'm going to have my set of numbers 1 through 2n. And I'm going to choose a subset of size n plus 1. This time my claim is that there exists 2 numbers a and b such that a plus b is equal to 2n plus 1. All right, so the trick now is what are the boxes going to be such that they all contain, I'm going to have n boxes, and the 2 numbers that go into my n boxes will always have this property. Right, so that's the idea. Again, we'll try and construct a counterexample using n equal to 4 and see if we can gain some insight. So let's say I start by choosing 1, right? So I mean that is sort of an arbitrary starting place. If I choose 1, then I can't choose 8, right? So my claim for n equal to 4 is a plus b is equal to 2 times 4 plus 1, or 9. So I can't choose 2 numbers. I'm trying to construct a counterexample, and in my counterexample, I want to avoid choosing 2 numbers that sum to 9. So if I choose 1, and 1 goes in my subset, then I can't choose 8 because 1 plus 8 equals 9. Okay, so then I still have these numbers to choose from. Let's say I choose 2, then that rules out 7, right? Because 2 plus 7 is equal to 9. If I then choose 3, well, that rules out 6. And then if I choose 4, well, that rules out 5. And now I've already selected all these numbers, and I cannot select these numbers lest this claim be true. So again, sort of a simple example, but I think we start to see the pattern here is basically if I want to find a pair of numbers A and B that sum up to 2n plus 1, I basically take the first and the last, and then the second and the second last, the third and the third last. All of these pairs sum up to 2n plus 1. So that's going to indicate what my boxes are supposed to be. All right. So we want n or fewer boxes. Each box is going to hold 2 elements. So yeah, if I have in general, so in the previous case, my boxes would have been 1 and 8, and then 2 and 7, 3 and 6, 4 and 5. So now I have n equal to 4 boxes, and I have a subset. Any subset of size 5 will have 1 box with at least 2 elements. And then more generally, for 2n elements, I can pair up 1 with 2n, 2 with 2n minus 1, 3 with 2n minus 2, all the way down to n and n plus 1. So the 2 middle elements, that would be this guy. Okay, so I have my n boxes. I have my subset of size n plus 1. By the pigeonhole principle, one of these boxes must contain at least 2 numbers, and those 2 numbers will sum up to 2n plus 1. Okay. Questions? All right. Let's be a little more clever now. There exists numbers a and b such that a is a multiple of b. The exact same scenario, I have 2n numbers. I have a subset of size n plus 1. And my claim is that there's 2 of them such that a is a multiple of b. So again, we'll try and construct a counterexample. This one seems a little more complex, though. It's going to require a little bit more clever manipulation, but we'll start in the same place. Take n equal to 4, the numbers 1 through 8, and I want a subset of size 5. But now I want to try and construct an example that this is not true of, which means that I can't take 1 because 1 is a multiple of everything. So my subset cannot contain 1. I can start at 3, right? I kind of want to avoid 2 as well, since 2 is an even number and it divides all even numbers. So that's going to wipe out a bunch of my choices if I take 2. So let's start at 3. So I take away 3, and that means I can't use 6. I take away 5. Well, 5 is a prime number, and 5 doesn't divide anything, so that's a good choice. I'm going to add 7. 7 is also a prime number, and nothing divides it. I have 3 numbers here. Now I kind of have to take, I can't take 1. I kind of have to take an even number. Let's try 4. If I take away 4, that means I can't take 2, and I can't take 8. Seems that any even number gives us this problem. So yeah, now I have chosen these 4 numbers, and the other 4 numbers are not available. So sort of gives us an idea maybe of how to make our boxes, right? So, even numbers, or I guess numbers that are multiples of 2, are particularly bad. They basically all divide each other, which yeah, maybe that gives us a hint. So our odd numbers are sort of a little more unique. When I choose 7, for instance, nothing divides it because it's prime. If I had a big enough set, it might divide into 14 or something, or 21 or whatever. But so odd numbers, prime numbers, these are good candidates. But yeah. out of options. Incidentally, anybody have any ideas of how you could prove this? Yeah.
You could start with the high numbers and work and compare them with lower numbers that they're a factor of.
Yeah.
Factor of them. And then, so in this example, you would have 8 and 1. Well, actually, you'd have 7 and 2. Okay, I'm actually not sure how you.
No, but yeah.
Yeah, with amplify the after you take 5, 6, 7, and 8.
Yeah. Well, yeah, there's something special about the odd numbers for sure. They're a little more resilient to being divided. The even numbers are a nightmare. They're all, but yeah, you have the right idea. You try to formulate an example, and then you run into a problem. Maybe it didn't consider this case, right? So you want to generalize this as much as possible. But yeah, it's a good try. Yeah. 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 Something that can't be broken down. So those are prime numbers, but they're hard to find, eh? So if I'm talking in general, 2n, find all the prime numbers in there. That's not an easy task. If n is big, it's going to be. So maybe prime numbers is a little too far. Maybe we want to stick with odd numbers. Yeah. That's true. An interesting idea. That probably I think there's a solution around that somewhere, but I don't. So the trick is now I have to prove that one of those lower numbers. Well, I guess 2 would divide them, eh? So maybe that works. But you have to choose, you have to show that. Well, not really, right? So 1 times 2 is equal to 2. That is sort of you can divide all the even ones, of course, you can rule out. Well, no, that's not even completely true. I don't know. That's a hard problem. No, it's good though. I wouldn't know the answer unless I read it. So, I mean, these are all good ideas. So I'll show you the actual idea, and it has to do with, well, we really want to focus on how many odd numbers are in this set, right? So the even numbers are kind of going to be easy to divide, but the odd numbers are going to be a little bit more difficult. So, right. So we're going to take our subset S that consists of n plus 1, and we're going to break it down and use some really ugly math notation. Don't be afraid of this. This is just, I'm going to say, well, every number, if it's even, then it is some multiple of 2, right? So that's 2 to the ki times some odd number. Like eventually you'll get down to an odd number. If it's a power of 2, then that odd number is 1. But well, we'll look at some examples here. So if I take the number 48, well, that is basically, if I keep dividing by 2. So I take 48 divided by 2 is equal to 24. And then I divide 24 by 2, that's equal to 12. And I divide 12 by 2, and that's equal to 6. I divide 6 by 2, and that's equal to 3. So I divided by 2 4 times, which is my 2 to the power 4. And then I'm left with this odd number 3. Okay, so that's how we're going to break down all of our numbers that way. And of these numbers, this part is not super important. It's a power of 2, which means that basically any two powers of 2 are divisible by each other, right? So 2 to the 1 is equal to 2, 2 to the 2 is equal to 4, 2 to the 3 is equal to 8, 2 to the 4 is equal to 16. And I could take any two of those numbers and one is divisible by the other, right? Because they're all powers of 2. So that's gonna, break things down into the easy case, which is the powers of 2, times the harder case, which is the odd numbers. It's going to be harder to find an odd number that can divide that. But that's how we're gonna break them down. Some more examples. Well, if my number is odd, of course, all I care about is the odd component. So then this is times 2 to the 0. So if it's an odd number, I just use the number itself. If it's even, I divide by 2 until I get to an odd number. And then what I really care about are these odd components. Okay. So yeah, odd numbers are all times 2 to the 0. Anything that's a power of 2, the even component, or sorry, the odd component is 1. So yeah, these are just a bunch of examples. Okay, so now that I can express all of these numbers as some power of 2 times an odd component. Well, and then I look at all of the odd components, right? So every single number in my subset has some odd component, either 1 or 3 or 5 or 7 or whatever, but it's in there. And there are, since I have n plus 1 numbers, these have n plus 1 odd components. So, and these odd components are, I'm going to select them from some set, but so how big is that set? So these are factors, which means, yeah. Well, so the set has to be at most 2n. So you're close. Well, the set of odd factors. Right, exactly. So there is only n odds. If you think about it, the odd components can be I can't have anything bigger than 2n. Yep. Exactly, yeah. So all of my odd numbers come from, I'm just going to take this set and every odd number from it, and any odd factor has to come from this set, right? So I have the numbers themselves, which could appear, but any factor has to be less than the maximum, which is 2n. So any odd factor can be at most 2n minus 1. So I have a finite sized set of odd numbers to choose from, and this set has size n. If I count them all up, it's basically, I have 2n in my original set and I take every second one. So that leaves me with n in this set. And yeah, and then by the pigeonhole principle, we know that while I have n plus 1 odd components, that these are, the odd factors of these numbers. And I'm choosing from a set of size n, so 2 of them must have the same odd component. Okay. So, yeah. So yeah, by the pigeonhole principle, I have 2 numbers, number AI and number AJ, such that their odd components are equal. All right, questions? Everybody following? Yeah. Right, so this is in general the number of odd numbers. So let's very quickly talk about this specific example. Right, so that is if my n is equal to 4, oops, then that is my set, or sorry, I'm taking a subset of this. So my S is a subset of these numbers. That means my odd numbers in this case are 1, 3, 5, 7. Right, so this is, in this case, this is my 2n minus 1 if n is equal to 4. So I'm just taking, this is my original set of numbers 1 through 2 to the n. I'm taking a subset of that of size 5. If I look at all of the odd numbers, all of the possible odd components, they are chosen from this set of size n. So just every odd number in my set. Yeah. They can't be bigger than that because then that means the resulting number would not be in that set. Oh yeah, the claim here is true. Yeah. But we're still gonna prove it. So yeah, other questions? Okay. All right, so we have two numbers taken from this set, or sorry, from this subset that have the same odd component. So we'll call them numbers I and j. If they have the same odd component and then they're multiplied by some power of 2, well, when I divide one by the other, right, I get, these will cancel out because they're the same. And then I get some power of 2 divided by some power of 2. And as we talked about it, I didn't really prove it or anything, but any power of 2 can divide any other power of 2, right? It's just the way the powers of 2 works. So the result is if I divide AI by AJ, I end up with some power of 2 as a result. So they divide each other evenly. Right, so therefore AI is a multiple of AJ, and yeah, we proved that using the pigeonhole principle. Now in a slightly more clever way, I guess. But yeah, questions? Yeah. Right. Yeah. Yeah, they have the same remainder. Does that help? I mean, yeah, are you trying to solve this problem with remainders? Yeah. Divided by, so the remainder is divided by 2n. And so it's going to be some number. Divided by same, yeah, you're right, divided by n. And then you get, well, yeah, now you have n minus, or now you have n boxes, I guess, 0 to n minus 1. And then I don't know how you prove they're divisible by each other, though. That's the tricky part. Yeah, but that's, yeah, I don't know. I mean, maybe there's something there. I just don't know. All right, we can talk about that after and see. If you like remainders, you'll love Euclid's algorithm, which we'll take. Any other questions? Yeah.
Yeah, so we're just gonna get today, non-famous guy.
Yeah.
I think some famous guy invented the pigeonhole principle. We don't know where his name. Who is he?
I would have to look that up. I don't know. Yeah, usually they're named after the guy, but maybe it was so common that everybody just knew it. Yeah, pigeonhole principle. Maybe there's not just maybe it's not a single person. Maybe a bunch of people came up with it independently, which happens. Yeah. All right. So we'll look at another example of, yeah, it's a little complicated, but yeah, we should be able to get through it pretty quickly. And then we can look at some of assignment 1 questions or some other easier examples. So here's another interesting application of, again, the pigeonhole principle. Kind of comes up where you wouldn't expect. But let's say that during the month of September, which has 30 days, one of your TAs drinks 45 bottles of beer and at least 1 bottle per day. Yeah. So what we want to show is that there exists some consecutive set of days during this month where the TA drinks exactly 14 bottles of beer for some reason. Right, so let's say that this is our month of September. This is our 30 days. It's possible that this TA has 1 day where they drink 14 bottles of beer. It's also possible that they drink 7 on 2 consecutive days, right? So then we get 14, a set of consecutive days where they drink 14 beer. It's possible that they have a run of 14 days. They have to drink at least 1 beer every day. So in this case, if they only drank 1 per day for 14 days, then there is a run where they drank exactly 14 bottles, right? And this applies, we're talking about beer here, but this applies to, I mean, you could easily adapt this to anything. So yeah, we want to prove that there exists some set of consecutive days where the TA drinks exactly 14 bottles. And this is sort of a, you know, a place where you would not expect the pigeonhole principle to come up, but it does. Okay, so is there any questions on what we're trying to solve? Okay. All right, so we're going to we're going to get the proper slides. I think I may have opened the wrong set. Just a second. Oh, I may have uploaded the wrong ones too, that means. Now it looks like we're going with the old ones. So I did adapt them, but all right, whatever. So funny story, I took my son somewhere where there was no internet and I worked on the slides there and I updated them, and then I expected when I came home, I opened them up and then I expected Dropbox to handle everything, but of course it didn't. So now we have the old ones, which are fine. I think they introduced an extra complication, which I don't like, but I guess I don't have access to the slides unless I go back and get my home computer. So let's say we're going to define a set BI. These are the number of bottles drank on any given day. But I kind of want you to not focus so much on BI. I want you to focus on, yeah, all right. I want you to focus on these AIs. So I guess I'm going to have to just roll with this, I guess. All right, so BI is the number of bottles drank on any given day in September, right? So B2 is the number of bottles drank on September 2nd. B3 drank on September 3rd. So if I sum up all of my B1 through B30, then I have 45. That's the, you know, that's my original, one of the, what do you call it? I don't know. One of the foundations, one of the premises that we're working with. And so we want to find a subsum of these that sums to 14. And we're going to define this second variable AI, and all this is the total number of bottles drank from September 1st to the 9th of September, inclusive. All right, so I really want to, you can almost ignore the BIs. And in fact, when I made the changes, I took them all out because they're, I think, unnecessary, but perhaps they help you. So these A1 through A30, these are the number of bottles I've drank up until that day, right? Including that day. And because the TA, I drank TA, this is a Freudian slip. So yeah, all of the bottles that I or the TA drank, because we have at least one bottle per day, all of these numbers are distinct, right? So two of them cannot be equal because each one has to be at least one more than the previous. So our goal then is to find two values, AI and AJ, such that the difference between them is 14. And if I can do that, then I've found a set of consecutive days where I or the TA has drank exactly 14 bottles. Yeah, and we could break it down into these BI plus 1 through BJ. That's, again, maybe trying to get away from too much, too much notation. But yeah, this is basically, simply put, this is all of the beer I drank on September I plus 1 plus I plus 2, all the way up to September J. And yeah, if the difference is equal to 14, that means these consecutive days I drank 14 beer, and we're done. All right, so that's what I got to prove. Questions so far? Okay. All right, so for example, this is September 15th, September 16th, 17th, and let's say that A14 is some number, and then I drank 14 bottles between A14 and A21. Then, September 21st, the number of beer I drank in total is equal to the number of beer I drank on the 14th plus the 14 in between. All right. Okay, so that's right. So if the difference between September 21st and September 14th, the total number of beer is 14, then I have some situation that looks like this, essentially. Okay. So what I'm going to do is I have my set. Let's back up a little bit. I have my set. I'm going to call this S1. This is all the numbers A1 through A30, right? So this is all of the beer I've drank up until that day, including that day. Then I'm going to define a second set, S2, and I'm going to add 14 to each of them. Plus 14, A3 plus 14, all up to A30 plus 14. Okay, so I have my two sets here, and each of them contains 30 numbers, and I'm going to take the union of these two sets, S1 union S2. So because I had 30 numbers in each of these sets, so together I have 60 numbers total. And out of these 60 numbers, well, which numbers can I choose from? Right, so and I mean, what is the highest possible value in S1 is A30, of course. And what is A30 equal to? Yeah, it's 45. So I have A30 equal to 45. And then I have A30 plus 14 in my second set. So that's going to be even higher. But it does have an exact value. It is 59. Okay. And what's the lowest possible number I can have in this set of S1 union S2? So it's 1. it's whatever AI or A1 is, right? That's the lowest number in this set. And it could be that A1 is 1. It has to be at least 1. Could be bigger, but it's definitely not smaller. So that means if I take all of the numbers in this set, I am taking them from this subset of 59 numbers. Okay. So what does that tell us? Yeah, so that means in my set S1 union S2, there are two numbers that must be the same. Okay, by the pigeonhole principle. Is everybody clear so far? Okay, so what do we know about these two numbers that are the same? Well, let's think about this. So I've mentioned it a few times that yeah, these are all distinct. So because the TA drinks at least one beer each day, none of these numbers A1 through A30 are the same. And that also implies that, well, I'm simply adding 14 here. That means none of these numbers can be the same either, right? That should be sort of obvious, I hope. So that means I have two numbers in this set S1 union S2 that are the same, but they can't both be from S1 and they can't both be from S2. So that means there's one number in S1 that is the same as one number in S2. Okay. Which, you know, this is that part clear? That's sort of the crux of the entire argument, is that I have one number from S1 and it's the same as a number from S2. All right, so what does that mean? Well, let's say by example, AI equals AJ plus 14, right? So my AJ plus 14 is equal to my AI. Well, I can rewrite that as AI minus AJ is equal to 14, right? Which was exactly what I wanted to show. I wanted to show that there were two numbers, AI and AJ, such that when I subtracted one from the other, they equal 14. And what that implies is that if I go from September J plus 1 up to September I and add all of the beer that I drank on all of those days, that adds to 14. Yep. Yep. All right, so I defined these variables A1, A2 up through A30. And what they are is A1 is the number of beer I drank so far in the month of September, including the first. And then A2 is the number of beer I drank in the month of September from the first to the second. So yeah, maybe I can go back and yeah. Let's throw a few more numbers in here. 1, 2, 3, 1, 1, and so on. So A1 is equal to 1 because that's how many I've drank so far. A2 is equal to 3, right? Because I've had 3 in total in this month of September. A3, I drank 3 more, so now my total is 6. A4, I drank another one, so now my total is 7, and so on. And I know that I drank 45 beer throughout this month, so that means A30 is equal to 45. And then, yeah, these are, and the B's are just simply what I drank on each individual day. Okay, so that's A1 through A30. A1 plus 14 through A30 plus 14 is simply, I take that number and add 14. So in this case, this is equal to 15. A2 plus 14 is equal to, what is that, 17. A3 plus 14 is equal to 20. And all the way up to A30, which is A30 plus 14 is equal to 59. Okay, so my S1 is all of these numbers, and my S2 is all of these numbers. So S1 union S2 is just a set of numbers from 1 to 59. And what we showed is that two of them were equal. The two that were equal could not both be in S1, and they could not both be in S2. That means I have some number. I wonder if one exists here. Well, no, not really. If I said, yeah, regardless, I have two of these numbers that are equal. So that means I have some I and j such that aj is equal to ai plus 14, or aj minus ai equals 14, and which is basically what we wanted, right? So if looking at this example, my aj would be A21, and my AI would be A14. And when I subtract the two, I get the 14 beer that I drank in between those two dates. All right, does that make sense? Other questions? Yeah. Yep. Yes. What's that? Sorry. Yeah. Yeah, it's just a consecutive set of days where there is exactly 14 beer drank. Yeah. If I chose 15, I guess then what happens? But if my claim is now that there's a consecutive set of days where I drank at least 15 beer. Can I prove that? Right, so let's say I take the same set, S1 is equal to A1, A2 up to A30. S2 is equal to now A1 plus 15, A2 plus 15, A30 plus 15. I still drank 45 beer in the month. But now my S1 union S2 is a subset of all of the numbers 1 up to 60. Right, so A30 is 45 plus 15 is equal to 60. So yeah, I have 60 numbers total and chosen from 60 numbers. So if I can't prove that I drank 15, exactly 15 in some consecutive set of days. That's the limit. I could choose 14 or 13 or something, but other questions? All right. So I didn't really like these, or I thought these slides were a little cluttered. I will get the other ones up. I don't know. I'll check to see if they're up on Dropbox, or they might have to wait till tomorrow. But yeah, so that's another example. There's something called the generalized pigeonhole principle, which is very similar to what we just did. But so let's take a nice simple example. We'll take 7 days in a week and say how many people were born on each day of the week. Or in this case, how many people do I need to have to guarantee that at least 5 people were born on the same day of the week? Right, so if I wanted to guarantee at least 2 people were born on the same day of the week, I need how many? Right. If the question was 2, right? So this is what we learned already. If I wanted to show that everybody was born on some day of the week, probably you don't know it, it's not that popular, but there's only 7 choices. Yeah, so if I have 8 people by the pigeonhole principle, then at least 2 people were born on the same day. But then how many people would I need to guarantee that at least 5 people were born on the same day? Should be where. Anyone, I don't know. 12? Not quite. I mean, you sort of have the right idea, but I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 guarantees 2. I would need more. Yeah. Yeah, exactly. 7, well, or pretty close to that. 7 times 5 would give me 35, and I would be guaranteed to have, I mean, yeah, I don't quite need 35. Yeah.
9, so 4 times 7 plus 1.
Yeah, exactly. So 29. So if and again, just by, I say, well, 1, 2, 3, 4, what's the most I can have without having 5? And that is 28, right? I have 4 born on each day. And then if I have one more, then one of them must have at least 5, right? So this sort of generalizes in that sense. So the first, and it's probably not too hard, but the first question on your assignment 2 is the generalized pigeonhole principle, or at least partially. Yeah, so the generalized pigeonhole principle, the statement of it would be if I place n objects into k boxes, there's at least one box with the ceiling of n over k, right? So in this case, I said 29 people into 7 boxes, and this gave me 4 1/7. And I take the ceiling of that because I can't place 1/7 of a thing in a box. So that means there must be a box with at least, how would I write that? I guess if I take the ceiling of that, then that's equal to 5. So I have one box that has at least 5 people in it. All right. The other way to state this, which isn't on these slides, but who was it, Dijkstra? I think it was Dijkstra that said the maximum is at least the average. So what does that mean? So I want to say, well, one of these boxes has the maximum number of people. And then my claim is that that maximum is at least the average number of people. That's a little more clever, but it still does work, right? So if I said the maximum is equal to the average, well, the average number of, if I have 29 people in 7 days, the average is 4 1/7, which means that the box with the most people or the day with the most people born on it is at least that value, right? Which means that I basically take the ceiling because I can't have a part of the thing. If it was 28, then the maximum is at least the average. Well, the average is 4, so then the maximum might be 4. It can be. It can be higher than that, but it's at least 4. All right, questions? Okay. What you guys want to take up some assignment 1 stuff? Or what, any questions you want to take in particular? I'll have to pull up assignment 1, I think, but. Yep. What's that, sorry? I'm hoping today. It's written, Pat's just proofreading it. I tend to make dumb typos and stuff, yeah. Yeah, so the last one with the 4 cages? Number 3 or number 4? The 4 really large cages, or else the 2 all dog? Yeah, okay. So, of course, for number 3 here, suppose n is even and we have m equals n over 2 cages. All of the dogs are black, so it's similar to this question, but now it's a little harder to count. So question 8 as well. Okay, yeah. I'll make sure I have time to get to question 8. So I might cover these a little quickly. I'll release these solutions to you today. I'm just sort of busy. So yeah, well, what can I do? Well, I mean, really the power is getting the correct procedure. Forget about the math. How do I have n dogs and I want to grab 2 of them and I'm going to put them in a cage? Right, so I have a kennel full of n dogs and I'm just going to run over. I'm going to grab 2 and I'm going to lead them into cage number 1. I'm going to close that cage. I'm done that one. So how many ways are there to do that? Well, there was n dogs in the kennel that I grabbed. I put them in cage 1. The next pair, I want to fill cage 2. I'm going to go back to the kennel. Now there's only n minus 2 dogs. I'm going to grab 2. Again, the order doesn't matter. They're both going in the same cage. I'm going to put them into cage 2. So that is n minus 2 choose 2. And then I'm going to go back, n minus 4 choose 2. And yeah, if you write it using the pi notation, or you can, I mean, you could have written it times n minus 2 choose 2 times, and then use the ellipses down to what, 2 choose 2. That would have also been fun, right? So it's, again, it's a bit ugly, but it's just, if you define the procedure correctly, you can do it. There are ways to sort of, yeah, there's a way you can map it to Mississippi, right? If you think of, maybe this is a little confusing, but if you think of all the dogs as being the locations that I can put my letters, and each cage is a pair of identical letters, then the number of ways I can map, I have to choose 2 of those dogs for cage 1, right? So that's the same as I'm choosing 2 locations for the letters for 2 instances of A, let's say. So it's, you can, that might be harder to visualize, but you can do that. The other thing you can do is you can line up all your dogs in a row, take all the take a permutation of them, and then I take the first 2, they go into cage 1, the second 2, they go into cage 2, etc. I double counted a bunch, right? Because now I have, whether this was D1 or D2 or D2 and D1, they're both going in the same cage. So I've double counted those instances. So then I can, you know, if I have something in order and I want to take the order away, I can divide by the factorial. So if I divide this by 2 factorial, and I divide this by 2 factorial, so essentially all permutations is n factorial divided by 2 factorial to the power n over 2, right? So there's n over 2 cages, and that's the number of times I've double counted. So you get something like this, which is exactly a multinomial of, yeah, anyway. Or you could have written it, so 2 factorial is the same as 2, so. But yeah, if you don't understand all of those, that's fine. This just brute force, that's acceptable. Questions? All right, let's make sure I can get through 10 minutes. I have at least 7 dogs and 4 really large cages. how many ways are there to place the dogs in the cages such that at least 2 cages are non-empty? So 2 cages non-empty. Geez, I find that wording so confusing. So that means I have at least 2 cages with dogs in them. Yeah, exactly. Yeah, so how is that? Which order? No, I mean, it only matters which dogs are in which cage. That's it. I don't care what order I put them in, right? No. So the way, if I have 4 cages and I am going to say, well, I'm going to put the dogs in the 4 cages in any combination. Well, then, yeah, in some sense, the procedure has an order, right? I take dog 1, I choose one of the 4 cages and I put them in it. I take dog 2, I choose one of the 4 cages and put them in it. And that is, so dog 1, I have 4 choices. Dog 2, I have 4 choices, up to dog n, right? So that is 4 to the n. And that's any old way, including, I have 3 empty cages, 2 empty cages, 1 empty cage, or no empty cages. Now we're going to say at least 2 cages are non-empty, which means that I want to eliminate the case where 3 cages are empty. I really hate the wording of that. But yeah, at least 2 cages are non-empty means at least 2 cages have dogs in them. So that means 2 cages can be empty, or 1 cage can be empty, or no cages can be empty. What I can't have is 3 cages empty, right? So this is all of the combinations. And from that, I want to subtract the number of ways I can have 3 cages empty. Of course, if I have 3 cages empty, all the dogs go into 1 cage. There is 1 way to do that for each of the 4 cages, right? So that means by the complement rule, there's 4 ways total to have that all dogs in 1 single cage. That's the case I want to eliminate. Make sense? Yeah. We're all what? No, yeah, the dogs have to go in a cage. Yeah. So each dog has to be in 1 cage, basically. Yeah, we can't have all those dogs running around, I guess. I don't know. Other questions? Yeah. Yeah.
Cages, then there are 3 cages, and there are 2 cages. This is some of that. Would that count, or are you still double counting?
It's going to be hard to do that. You can, because the inclusion, so how are you counting? So let's say I'm going to count all 4 cages have a dog in them, at least 1 dog. How do I count that now? It's not though, because that counts, there might be some empty cages. That counts all possibilities. So I have to, from that, I have to subtract. Yeah, if I'm counting it directly. So if I have a set that is no cages are empty, then I have to subtract. I do 4 to the end, but minus 1 cage is empty, and then minus 2 cages are empty, and then minus 3 cages are empty. You can do it that way, but you're going to get a lot of, you're going to end up with this at the end. You'll just have a lot of stuff canceling out. But yeah, I can't, counting no cages are empty is harder than you think, because you have to subtract a bunch of stuff that didn't happen. Yeah. Other questions? Yeah. 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 They're in different cages, then it's different. Yeah. Yeah. But yeah, you're counting them in the same order. So I just want to get to this last one. So the key here is I'm assigning all students exercises. The exercises are, I don't care, they're not numbered, right? They're just, I only care about the number of exercises you get, not which ones you get. So GI is the number of homework exercises that each student I gets. And the students get an average of 75 exercises each. So you can determine the total from that. So if their average is 75 exercises and there is 100 students, then I have 7,500 exercises total. Okay, and then from that, each student gets at least 50 exercises. So we have something along the lines of G1 plus G2 plus G3 is equal to 7,500, right? Plus G100. So 100 students, all of their exercises sums up to 7,500. We know how to solve that, right? This is just the solutions to a linear equation. The caveat now is that those have to be at least 50. So we also learned how to do that in class. I make a new variable GI prime that's GI minus 50. And then I simply add up G1 prime plus G2 prime up to G100 prime. And that's going to be equal to what? So I have G1 up to G100 summed up equals 7,500. Now G1 prime is equal to G1 minus 50. And this is true actually for all I. So GI prime equals GI minus 50. So on my left-hand side, I have a bunch of variables. I've subtracted 50 from each one, right? So that gives me in total 5,000 that I've subtracted. So this is 7,500 minus 5,000. Right, so now I have, and this, 2,500. Now I have this linear equation where these are at least 0. GI prime is going to be at least 0 for all I, and they sum to this value. Now I can figure that out. Well, the general formula is n plus k minus 1. Choose k minus 1, where k is equal to 100, n is equal to 25. So this is 25, 99, choose 99. Right? I mean, it's just a bigger example of what we saw in the notes. May have been last class. All right, questions on that one? Does that make sense? What's that, sorry? Oh, question 3. Like question 3? Oh, the drinking one? Yeah, we might be running out of time. The one that people seem to have the most problem with was number 2. It's the same as number 1, but now I have 3 factorial permutations, right? In the first case, he started with 1 bourbon, had 1 scotch, 1 beer, but now I might have a beer, scotch, bourbon instead. Yeah. Yeah. Anyway, we can talk about this more next class if you guys want. That's it for today.
So, plus I saw